Swayam Prabha. Digital India. Educated India.
Namaskar. So, we are entering into the second week of our this course. So, in this week we will try to understand the mesh and nodal analysis of various electrical circuits, and today we will specifically discuss about the RMS voltage and current values, means how to identify, means how to derive these values, and how we can use these values in finding out the power output of a particular circuit. So, before going into the details, let us try to understand what we learned in the previous week. So, we started with the basic concepts of charge, then we spoke about the current, voltage, power and energy. Then we discussed about active and passive circuit elements, where we discussed about the voltage and current sources, and we also saw what are the various symbols of dependent as well as independent voltage and current sources. Then we discussed the sinusoid and the phasor, how we can find out the value of phasor with the help of given sinusoid. Then we discussed circuit elements, that is resistance, inductance and capacitance. Thereafter, we discussed Ohm's law and Kirchhoff's law, which are the very basic and very important laws for the calculation of various current and voltage values in a given electrical circuit. So, most of the time you would be using either Ohm's law or the Kirchhoff's voltage or current law in there in your circuit analysis. Then we discussed about series and parallel circuits for resistor, capacitor and inductor. We also discussed current and voltage division. Then we discussed voltage and current phasor relationships for inductor and capacitor, and then we studied the instantaneous and average power calculation. So, today we will discuss the concept of root mean square voltage and current, which is also called as effective voltage or current. Now, the idea of effective value arises from the need to measure the effectiveness of a sinusoidal voltage or current source in delivering power to a resistive load. The effective value means the value for a periodic current that is equivalent to that DC current, which delivers the same average power to the resistor as the periodic current does. It means that to find out the effective value of AC current, we have to equate the power dissipated by an element when it is connected with AC source and the DC source. So, in that case, both when we connect this particular circuit to AC source and DC source, the power should be equal in both of the cases. So, we will equate the power consumed by the element when it is connected to AC and DC and try to find out what should be the value of effective current. Similarly, you can say that if you connect the AC voltage source, then how power would be dissipated by that particular element, and when we equate the power for DC and AC, we get the value of effective voltage. So, we will use that concept and we try to find out what is the value of effective voltage and current. So, now let us start with the average power definition. The average power says that power P is nothing but the value of 1 over T integral of P dt between 0 to T. Now, we know that the power P is nothing but V into I, and V can be replaced with I R, that is the according to Ohm's law, and then I, it means that it becomes I square R. So, this P dt can be equivalently represented as I square r. So, average power P can be given as 1 by T 0 to T I square r dt. So, if you see this particular value is coming from a particular AC source, means the suppose if you take a particular element, say let us take the resistor, and it is connected to one AC source and one DC source with the switch. So, you can toggle that switch between AC and DC. So, first if you are connecting to AC source, that means the switch is at this side, means in that case what would be the average power? Average power would be given by this particular equation. Now, instead of AC, if you are connecting that element to DC, you will get another the value of average power, but that would be absorbed by a particular element. In this case we have the resistor, but the source is DC. So, we have some power dissipated by the resistor would be, say we say that the current at this point is I effective. So, this will become P is nothing but I effective square R. Now, as per definition, our objective is to find out the effective value for the current. It means that the power value should be equated when the DC current is flowing and when the AC current is flowing. So, in that case what we can say? We can say P, which is I effective square R in this case, is nothing but equal to the 1 by T integral 0 to T I square R dt. So, now if you see this particular equation using the mathematical operations, you can simply say that I effective is nothing but under root of 1 over T and integral of 0 to T I square dt. So, this you can get from here. So, what you get from here? I effective is the current value, which is nothing but root of the mean of the square values. So, I square is the square value. So, you take the integral, means summation of all I square component, and then you take the mean, and then you take the under root of the complete output of this particular equation. So, I effective is nothing but root of mean square value of the current element. Similarly, the effective value for voltage can also be written. You have to just simply replace the current I when we are saying P is equal to V I. So, instead of writing the value of V in terms of I, you will write the value of I in terms of V, and you will get this equation. So, we can say that V effective is also similar to I effective, that is under root of 1 by T 0 to T V square dt. Now, we know that the sinusoid Vt is Vm cos omega t. This is we generally take as a starting point for deriving the various equations. So, let us take the same example for sinusoid, that is Vt is equal to Vm cos omega t. Now, if you put this value of V, because this is the instantaneous voltage and it is represented in the form of sinusoid. So, you will write V effective is nothing but 1 by T 0 to T Vm square cos square omega t, because there we have the V square term. So, this will become Vm square cos square omega t dt. Now, if you see this particular term, this is nothing but, if you recollect, we discussed cos A plus B is nothing but cos A cos B minus sin A sin B. Now, if you keep A and B both same, suppose in this case let us say A is also omega t, B is also omega t. So, this will become cos of 2 omega t, and that will become cos square omega t minus sin square omega t. Now, if you add cos square omega t and subtract also with the same term, that is cos square omega t, it will not have any impact on the overall equation. Now, what you will do? You add these two terms, it will become 2 cos square omega t minus of sin square omega t plus cos square omega t. Now, if you see this expression, the value of this expression is 1. So, this will simply become 2 cos square omega t minus 1. Now, if you rearrange, what you will get? Cos square omega t is nothing but 1 plus cos of 2 omega t divided by 2. So, this value which we have just derived, you can put in place of cos square omega t. So, since Vm is the constant term, you can take out from the integral, it will become Vm square by t 0 to t 1 by 2 1 plus cos 2 omega t dt. So, now if you see this particular expression, what you will get? Since this is a sinusoidally varying term, so the value of this term over one particular time period, that is between 0 to t, will become 0. So, eventually what we have left with is only term 1. So, if you simplify just by integrating dt, this particular constant term with dt, you will get the output as Vm by root 2. So, what you have got now is that the RMS value of voltage. Why it is RMS? Because from the initial convention we have seen that this particular value is nothing but root of square of the mean value. So, here square value is there, you sum up and take the mean and take the under root of the term. So, this will become the root mean square value, that means square root of the mean of the square of the periodic signal. So, in this case this periodic signal is V. So, the output which we get from here is V RMS, and this value is equal to Vm by root 2, and Vm is the peak value of the signal. Similarly, if you take current, that is IT, and we represent IT in terms of sinusoid as Im cos omega t, we will get the RMS value of current, that is IRMS equal to Im by root 2. Now, you have to note the important point here, that this particular the value is applicable only for sinusoidal signals. If you do not have sinusoidal signal, it means that you have to compute from the integral and then calculate the complete RMS value with the help of the original function which we just used for derivation of RMS value. So, now from the previous lectures we can recollect that the average power absorbed by a circuit under sinusoidal excitation can be represented as P is equal to 1 by 2 Vm Im cos theta V minus theta I. Now, how you can represent in the form of RMS values? You have to just simply take this particular value of 2 in two forms, that is you can write root 2 into root 2 and you put these root 2 below the value of Vm and Im. So, then it will become average power P is nothing but Vm by root 2 into Im by root 2 cos of theta V minus theta I. Now, this is the RMS value which we just derived, and similarly Im by root 2 is also the RMS current we just saw. So, average power you can write as Vrms into Irms cos of theta V minus theta I. Now, this is the general expression. If the circuit element is purely resistive, it means that the theta I will be equal to theta V, because your current and voltage both phasor will be in phase. So, in that case theta V minus theta I will become 0, and finally, the average power absorbed by the resistor would be 1 by 2 Vm Im, that can be written as I square I RMS square R or Vrms square by R. So, when the sinusoidal voltage or current is specified, it is often specified in terms of its maximum value or the RMS value, because its average value will always be 0. Being a sinusoidal, you will always get the average value of either voltage or current as 0. So, that is why it is not advisable to keep the to put the value of voltage and current in terms of average value. That is why you will always see either the value of voltage and current is specified as maximum or RMS value. But in our day to day life, the power industries specify phasor magnitude in terms of their RMS values rather than the peak values. So, that is why the RMS term is very common. It is mostly used in almost all communications when we talk about the various voltage and current signals in the electrical engineering or in the power system area. Say for example, if you see 230 volt which is coming to every household, this is RMS value, not the peak value. So, whenever we say that the voltage in our house is 230 volt, it implies that you are talking about the RMS value, not the peak value. It is convenient in power analysis to express voltage and current in their RMS value, because it is more convenient to do the calculations, and the power calculation we just discussed is also easy when we use the RMS value. And our other measuring instruments like voltmeter and ammeter are designed to read the RMS value directly. So, that is why the RMS value is very important for our circuit analysis. Now, let us take one example so that you can understand the phenomena. Let us see that there is some voltage Vt, that is 10 sin t, which is shown in this figure. It is half wave rectified, means the negative value is not there, and we want to find the average power dissipated in a 10 ohm resistor. So, if you see this figure, you will come to know that the time period of this particular waveform is also 2 pi, and the voltage is defined as 10 sin t for 0 to pi, and it is 0 between pi to 2 pi. So, how you will calculate the RMS value? Since it is not a pure sinusoidal, you cannot directly use Vrms is equal to Vm by root 2. You have to calculate with the help of the standard definition of root mean square. So, Vrms square is nothing but 1 by t, 0 to t V square dt. You put the value of voltage value, that is 10 sin t for 0 to pi and 0 for pi to 2 pi. So, what you will get when you calculate and you basically simplify, you will get RMS value of voltage as 5 volt. So, the average power absorbed by the resistor, you can say that P is nothing but Vrms square by R. So, here RMS value which we derived is 5 volts. So, Vrms square is 25. resistor value is 10. So, output would be 2.5 watt. Let us take another example. Suppose the signal is like this, which is shown in the figure. Between 0 to 2 it is triangular wave, and between 2 to 4 it is square wave. So, the period of the waveform is 4, and waveform can be defined as, because we are talking about the current IT. So, IT can be defined as 5t between 0 to 2 and minus 10 between 2 to 4. So, how we can calculate RMS value? IRMS would be 0 to 1 by t, 0 to t I square dt under root, and simply put the value of current I for 0 to 2 and 2 to 4. So, in that case, when you will simplify this integral, you will get the output of IRMS as 8.165 ampere. So, when you get this current, you can simply put the value in the average power P, that is nothing but IRMS square R, and you will get the power absorbed by the resistor, that is 133.3 watt. Now, let us talk about another term called apparent power and the power factor. So, earlier what we derived was the average power absorbed by the circuit, which is excited by a sinusoidal signal, and we express them in the form of voltage, RMS voltage and current. So, power P was Vm by root 2 Im by root 2 cos theta V minus theta I. So, we wrote that expression as Vrms into Irms into cos theta V minus theta I. So, what you can do, you can rewrite the above expression as P is nothing but S multiplied by cos theta V minus theta I. What is S? S is called as apparent power because it is defined as a product of RMS voltage and current. So, if you correlate with the DC voltage source power, you see that in DC we define power as V into I. So, if you correlate, the apparent power would be the IRMS into Vrms, so that you get a feel of like this is apparent as compared with the DC source. So, it is apparent power because it seems apparent that the power should be the voltage current product, which is by analogy with the DC resistive circuit. Now, the apparent power is measured in volt ampere, just to distinguish it from the real power, because we say real power in terms of watts. So, just to differentiate between apparent power and the real power, we use volt ampere as a quantity for apparent power and watt as quantity for real power. Now, from the previous expression, you can also observe that apparent power needs to be multiplied by a factor to compute the real or average power. So, what was the term? That term was cos of theta V minus theta I. So, if you divide real power by apparent power, you will get one term called cos of theta V minus theta I, which is called as power factor in the mathematical terms. Now, this power factor ranges between 0 to unity. So, if you have the purely resistive load, the voltage and current would be in phase. In that case, theta V minus theta I will be 0. So, what will happen? In that case, the value of cos theta V minus theta I will be equal to 1. So, the power factor would be 1. So, that implies that apparent power is equal to the average power in this case. In case of purely reactive load, when theta V minus theta I is equal to 90 degree, so that can be either inductive load or the capacitive load, the power factor would be 0. So, in this case your average power would be 0. So, these are the two extreme cases in which power factor is said to be either leading or lagging. Leading power factor means that current leads voltage, which implies that it is having the capacitive load, while in case of lagging power factor it means that current lags voltage and that implies an inductive load. So, this particular aspect you will keep on using in your circuit analysis, because the circuit will compose of resistor, capacitor, inductor, all components would be there. So, when you will say that current is leading with respect to voltage, it means that the circuit is capacitive, or when the current is lagging with respect to voltage, you will say the circuit is inductive. So, in that case, when you have capacitive circuit, you will have leading power factor, when you have inductive circuit, then you will have lagging power factor. Now, let us take one example. Suppose a series connected load draws current given by this expression I t, when the applied voltage is V t, that is 120 cos 100 pi t minus 20. Now, we have to find out the apparent power and power factor of a load and determine the value of element from the load. Now, the apparent power would be Vrms into Irms. So, from since these both are sinusoidal waveforms, you can simply use the values like Vrms would be Vm by root 2 and Irms would be Im by root 2. So, just put the values of Vm and Im and simplify, you will get apparent power as 240 volt ampere. Now, power factor you can simply calculate with the help of these two expressions, because power factor is nothing but cos of theta v minus theta I. Here theta v is minus 20 degree and theta I is 10 degree. So, you will get power factor as cos of minus 30, that is nothing but 0.866. Here power factor is leading because current leads the voltage. Here the phase angle is positive and for voltage the phase angle is negative, that you can easily visualize that current is leading with respect to voltage. So, it means that the circuit is capacitive. So, load impedance can be calculated by this formula, that is Z is nothing but V by I, and you put the value of V and I that is in the form of phasors. So, that is 120 angle 20 degree divided by 4 angle 10. If you simplify, you get Z value in phasor form as 30 angle minus 30. Now, if you convert into the rectangular form, you will get the value as 25.98 minus J 15 ohm. From this, if you correlate with respect to the term called R plus Jx, you will get that the Z is composed of 25.98 ohm as a resistive load and in series with capacitor whose impedance is Xc, that is equal to minus 15. So, using this expression you can simply find out the value of capacitance, that comes out to be 212.2 microfarad. Now, let us come to another term called complex power. Given the phasor that is V equal to Vm angle theta v and I is equal to Im angle theta I. So, that is nothing but V is Vm cos omega t plus theta v and I is nothing but Im cos omega t plus theta I. So, we represent V and I in the form of phasors, because these phasors are for voltage and current which is sinusoidally varying. So, complex power is nothing but the power S which is absorbed by the AC load, and it is the product of voltage and complex conjugate of the current. So, how we will write complex power S? S is nothing but 1 by 2 V into I conjugate. I conjugate means the IRMS value would now will become IRMS angle, instead of theta I it will become minus theta I. So, we will write the complex power as V I conjugate, that is V RMS into I RMS conjugate. V RMS will remain same, I RMS magnitude will be here, but angle would be now theta V minus theta I. So, you may ask that why this particular complex power is in the form of conjugate, because you are putting value of current as a current conjugate, not the voltage as a conjugate. The reason is that if you compare it with the average power we calculated, we got the term of theta V minus theta I. So, that particular average power we calculated with the help of the fundamentals of the trigonometric equations, that is the voltage we took in the sinusoidal form, current we took in the form of sinusoidal form, and when we analyze that particular value of average power, we got value of average power as 1 by 2 Vm Im cos of theta V minus theta I. So, since we already have that particular quantity derived, if we put V as a conjugate and not I as a conjugate, we will get this term as theta I minus theta V, which would be contradictory to what we derived in previous case for the average power. That is why we use V I conjugate, not V conjugate I. So, the conjugate is not having any physical interpretation or physical significance in this particular equation. This is just a mathematical representation, so that we can represent the equations effectively. Now, you can notice that the magnitude of complex power S is apparent power, because if you see this term V RMS into I RMS, this is our apparent power. So, if you write into rectangular form, the complex power is nothing but V RMS I RMS cos theta V minus theta I plus j V RMS I RMS sin theta V minus theta I. This is something which we have already derived, and that is called average power or real power, and this is the imaginary term which we have got in derivation of the complex power. So, complex power, the apparent power, complex power is also measured in the volt ampere, as we saw in case of apparent power. Just to distinguish between real power, that is what we measure in watts, we measure complex power in terms of volt ampere. So, let us look at the expression once again. V RMS I RMS cos theta V minus theta I would be the real power, and j V RMS I RMS sin theta V minus theta I will be written as j q. So, here the real term is P, which represents the average power delivered to the load and is only the useful power in the system, while the imaginary term Q is known as reactive power and represents the energy exchange between source and the reactive part of the load. So, if you see the equation, your reactive power would not be contributing in the overall power calculation when you have only the resistive load, because in this case theta V minus theta I will become 0 and sin theta 0 sin 0 will be 0. So, in that case you will have V RMS I RMS only the term for purely resistive load. Similarly, for purely capacitive and inductive, you will only have this term, that is the reactive power. So, it means that the reactive power is only visible when we have either capacitive or inductive load available in the circuit. Now, Q is measured in volt ampere reactive, just to distinguish it from real power P, which is measured in watt. Now, in standard practice, the S, P and Q are represented together with the power factor angle, that is theta is nothing but theta V minus theta I, using power triangle. And how we represent power triangle? Power triangle is nothing but the relationship between P, Q and S, and the angle between P and S is the theta degree, which is nothing but the power factor angle. So, this power triangle is very important, and most of the time you will be asked to show what is the power triangle. So, you should remember that the power triangle is nothing but this particular triangle where we correlate real power, reactive power and the complex power. So, with this we close our today's session, and in the next session we will discuss more about the other circuit aspects, like what is mesh, what is node, and then we will further build up the relationship for calculation of various electrical circuit parameters. Thank you.